Phew! We just completed our exploration of software-defined networking, and now we're jumping into traffic engineering.
Traffic engineering is a fancy way of describing how network operators deal with large amounts of data flowing through their networks. Companies like Google are doing exciting work in this area, so be sure to pay attention to the instructor notes section, where we'll highlight exciting research papers.
This lesson covers traffic engineering. Traffic engineering is the process of reconfiguring the network in response to changing traffic loads to achieve some operational goal. A network operator might want to reconfigure the network in response to changing loads to, for example, maintain traffic ratios in a peering relationship, or to relieve congestion on certain links in the network, or to balance load more evenly across the available links in the network. In this lesson, we will explore different ways of performing traffic engineering. We will start by looking at conventional approaches to traffic engineering, and we'll explore how software-defined networking is used to make the process of traffic engineering easier in both data center networks and transit networks. IP networks must be managed. Now, in some sense, IP networks manage themselves. There are several examples of protocols on the Internet that, in some sense, manage themselves. TCP senders send less traffic during congestion, and routing protocols will adapt to topology changes. The problem is that even though these protocols are designed to adapt to various changes, the network may not run efficiently. There may be congested links when idle paths exist, or there might be a high delay path that some traffic is taking when a low delay path in fact exists. So a key question that traffic engineering tries to address is how routing should adapt to traffic. In particular, traffic engineering attempts to avoid congested links and satisfy certain application requirements, such as delay. These are, in some sense, the essential questions that traffic engineering attempts to answer. In the rest of this lesson, we will look at how network operators can tune routing protocol configuration to affect how network traffic traverses the links in the network. And in particular, we will look at both intra-domain traffic engineering, that is, how to reconfigure the protocols within a single autonomous system to adjust traffic flows, as well as inter-domain traffic engineering, or how to adjust how traffic flows between autonomous systems. We will also look at multipath routing and how it is used to achieve various traffic engineering goals. Let's start by looking at how network operators can tune static link weights in a routing protocol like OSPF or ISIS to affect how traffic flows through the network. Let's assume that we have a single autonomous system with static link weights as shown. In such a setup, routers will flood information to one another to learn the network topology, including the link weights, on links connecting individual routers. An operator can affect how traffic flows through the network by configuring the link weights. By changing the link weight configuration, an operator can affect the shortest path between 2 points in this graph, thus affecting the way that traffic flows. In the link weight setting shown here, traffic would flow along the green path. Suppose that the operator would like to shift traffic off of a congested link in the middle of the network, such as this one. By changing the link weight from 1 to 3, the shortest path between this node and this node now takes an alternate route. So we can see from this simple example that by adjusting the link weights in an intra-domain topology, the operator can affect how traffic flows between different points in the network, thus affecting the load on the network links. In practice, network operators set these link weights in a variety of ways. One could set the link weights inversely proportional to capacity, proportional to propagation delay, or the operator might perform some network-wide optimization based on traffic. Traffic engineering has 3 steps: measuring the network to figure out the current traffic loads, forming a model of how configuration affects the underlying paths in the network, and then ultimately reconfiguring the network to exert control over how the traffic flows through the network. An operator might measure the topology and traffic, feed the topology and traffic to a what-if model that predicts what will happen under various types of configuration changes, decide which changes to effect on the network, and then ultimately control the network behavior by readjusting link weights. So in summary, we have measurement, modeling, and control. Each of these three components requires a significant amount of heavy lifting to make both practical and accurate in practice. Intra-domain traffic engineering attempts to solve an optimization problem where the input is a graph G, where R is the set of routers, and L is the set of unidirectional links. Each link L also has a fixed capacity. Another input is the traffic matrix, or the offered traffic load, where Mij represents the traffic load from router I to router J. The output of the optimization problem is a set of link weights, where WL is the weight on any unidirectional link L in the network topology. Ultimately, the setting of these link weights should result in a fraction of the traffic from I to J traversing each link L, such that those fractions satisfy the network-wide objective function. Defining an objective function is tricky. We could talk about, for example, minimizing the maximum congested link in the network, evenly splitting traffic loads across links, and so forth. What we'd like to represent is that the cost of congestion increases in a quadratic-like manner as the loads on the links continue to increase, ultimately becoming increasingly expensive as link utilization approaches 1. Solving the optimization problem, however, is much easier if we use a piecewise linear cost function. We can define utilization as the amount of traffic on the link divided by the capacity, and our objective might be to minimize the sum of this piecewise linear cost function over all the links in the network. Unfortunately, solving this optimization is still NP-complete, which means that there's no efficient algorithm to find the optimal setting of link weights, even for simple objective functions. The implications of this are that we have to resort to searching through a large set of combinations of link weight settings to ultimately find a good setting. So clearly searching through all the link weights is suboptimal, but the graphs turn out to be small enough in practice such that this approach is still reasonably effective. In practice, we also have other operational realities to worry about. For example, minimizing the number of changes to the network. Often, changing just one or two link weights is enough to achieve a good traffic load balance solution. Whatever solution we come up with must be resistant to failure, and it should be robust to measurement noise. We also want to limit the frequency of changes that we make to the network. This completes our overview of intra-domain routing, and now we will take a look at inter-domain routing. Intra-domain routing and traffic engineering concerns traffic flow within a single domain, such as an ISP, a campus network, or a data center. In contrast, inter-domain routing and inter-domain traffic engineering concerns routing that occurs between domains, something that we looked at before in the context of the Border Gateway Protocol. Before we proceed with our discussion of inter-domain traffic engineering, let's take a brief quiz reminding ourselves about the differences between intra-domain routing and inter-domain routing. Which of the following are examples of inter-domain routing? Peering between two internet service providers, peering between a university network and its ISP, peering at an internet exchange point, routing inside a data center, or routing across multiple data centers. Please again check all that apply. Peering between two ISPs involves inter-domain routing, as does peering between a university network and its ISP, or any peering at an internet exchange point for that matter. Routing between multiple data centers typically involves routing in the wide area, and hence may involve inter-domain routing. Routing within a single data center concerns routing in a single domain, and hence does not concern inter-domain routing. Inter-domain routing concerns routing between domains or autonomous systems. It involves the reconfiguration of the Border Gateway Protocol policies or configurations that are running on individual routers in the network. Changing BGP policies at these edge routers can cause routers inside an autonomous system to direct traffic to or away from certain edge links. We can also change the set of egress links for a particular destination. For example, an operator of Autonomous System 1 might observe traffic to destination D traversing the green path. But by adjusting BGP policies, the operator might balance load across these two edge links or shift all of the traffic for that destination to the lower path. An operator might wish to use interdomain traffic engineering if an edge link is congested, if a link is upgraded, or if there's some violation of a peering agreement. For example, AS1 and AS2 might have some agreement that they only send a certain amount of traffic load over that link in a particular time window. If the load exceeds that amount, an operator would need to use BGP to shift traffic from one egress link to another. Effective interdomain traffic engineering has three goals. One is predictability. In other words, it should be possible to predict how traffic flows will change in response to changes in the network configuration. Another goal is to limit the influence of neighboring domains. In particular, we'd like to use BGP policies and changes to those policies that limit how neighboring ASs might change their behavior in response to changes to the BGP configuration that we make in our own network. And finally, we'd like to reduce the overhead of routing changes by achieving our traffic engineering goals with changes to as few IP prefixes as possible. To understand the factors that can confound predictability, let's look at how the interdomain routing choices of a particular autonomous system can wreak havoc on predictability. Let's suppose that a downstream neighbor is trying to reach the autonomous system at the top of this figure. The AS here might wish to relieve congestion on a particular peering link. To do so, this AS might now send traffic to that destination out a different set of autonomous systems. But once this AS makes that change, note that it's choosing a longer AS path, now taking a path of 3 hops rather than 2. In response, the downstream neighbor might decide not to send its traffic for that destination through this autonomous system at all, thus affecting the traffic matrix that this AS sees. So all the work that went in to optimizing traffic load balance for this AS is for naught, because the change that it made effectively changed the offered traffic loads and hence the traffic matrix. One way to avoid this type of problem and achieve predictable traffic flow changes is to avoid making changes like this that are globally visible. In particular, note that this change caused a change in the AS path length of the advertisement to this particular destination from 2 to 3. Thus, other neighbors, such as the downstream neighbor here, might decide to use an alternate path as a result of that globally visible routing change. By avoiding these types of globally visible changes, we can achieve predictability. Another way to achieve effective interdomain traffic engineering is to limit the influence of neighbors. For example, an autonomous system might try to make a path look longer with AS path prepending. If we consider treating paths that have almost the same AS path length as a common group, we can achieve additional flexibility. Additionally, if we enforce a constraint that our neighbors should advertise consistent BGP route advertisements over multiple peering links, should multiple peering links exist, that gives us additional flexibility to send traffic over different egress points to the same autonomous system. Enforcing consistent advertisements turns out to be difficult in practice, but it is doable. To reduce the overhead of routing changes, we can group related prefixes. Rather than exploring all combinations of prefixes to move a particular volume of traffic, we can identify routing choices that group routes that have the same AS paths, and we can move groups of prefixes according to these groups of prefixes that share an AS path. This allows us to move groups of prefixes by making tweaks to local preference on regular expressions on AS path. We can also focus on the small fraction of prefixes that carry the majority of traffic. 10% of origin ASs are responsible for about 82% of outbound traffic. Therefore, we can achieve significant gains in rebalancing traffic in the network by focusing on the heavy hitters. In summary, to achieve predictability, we effect changes that are not globally visible. To limit the influence of neighbors, we enforce consistent advertisements and limit the influence of AS path length. And to reduce the overhead of routing changes, we group prefixes according to those that have common AS paths and move traffic in terms of groups of prefixes. Another way to perform traffic engineering is with multipath routing, where an operator can establish multiple paths in advance. This approach applies to both intra-domain routing and inter-domain routing. The way this is done in intra-domain routing is to set link weights such that multiple paths of equal cost exist between two nodes in the graph. This approach is called equal cost multipath. Thus, traffic will be split across paths that have equal cost through the network. A source router might also be able to change the fraction of traffic that's sent along each one of these paths, sending, for example, 35% along the top path and 65% along the bottom path. It might even be able to do this based on the level of congestion that's observed along these paths. The way that the router would do this is by having multiple forwarding table entries with different next hops for outgoing packets to the same destination. So quickly, how can a source router adjust paths to a destination when there are multiple paths to the destination? Dropping packets to cause TCP backoff, alternating between multiple forwarding table entries to the same destination, or sending alerts to incoming senders whenever a route changes. A source router can adjust traffic over multiple paths by having multiple forwarding table entries for the same destination and splitting traffic flows across the multiple next hops depending on, for example, the hash of the IP packet header. Let's now talk about data center networking and how network operators perform traffic engineering inside a data center. First of all, what characterizes a data center? Data center network has three important characteristics. One is multi-tenancy. Multi-tenancy allows a data center provider to amortize the cost of shared infrastructure, but because there are multiple independent users, the infrastructure must also provide some level of security and resource isolation. Data center network resources are also elastic, meaning that as demand for a service fluctuates, the operator can expand and contract these resources. It also can be pay-per-use, meaning that as the need to use more resources arises or disappears, a service provider can adjust how much resources are devoted to the particular service running in the data center. Another characteristic of data center networking is flexible service management, or the ability to move work or workloads to other locations inside the data center. For example, as load changes for a particular service, an operator may need to provision additional virtual machines or servers to handle the load for that service, or potentially move it to a completely different set of servers inside the infrastructure. This workload movement and virtual machine migration essentially creates the need for traffic engineering solutions inside a data center. A key enabling technology in data center networking is the ability to virtualize servers. This makes it possible to quickly provision, move, and migrate servers and services in response to fluctuations in workload. But while provisioning servers and moving them is relatively easy, we must also develop traffic engineering solutions that allow the network to reconfigure in response to changing workloads and migrating services. Some of the challenges for data center networking include traffic load balance, support for migrating virtual machines in response to changing demands, adjusting server and traffic placement to save power, provisioning the network when demands fluctuate, and providing various security guarantees, particularly in scenarios that involve multiple tenants. To understand these challenges in a bit more detail, let's take a look at a typical data center topology. A topology typically has three layers: an access layer, which connects the servers themselves, an aggregation layer, which connects the access layer, and then the core. Historically, the core of the network has been connected with layer 3. But increasingly, modern data centers are connected with an entire layer 2 topology. A Layer 2 topology makes it easier to perform migration of services from one part of the topology to another, since these services can stay on the same Layer 2 network and hence would not need new IP addresses when they moved. It also becomes easier to load balance traffic. On the other hand, a monolithic Layer 2 topology makes scaling difficult, since now we have tens of thousands of servers on a single flat topology. In other words, Layer 2 addresses are not topological, so the forwarding tables in these switches can't scale as easily because they can't take advantage of the natural hierarchy that exists in the topology. Other problems that exist in this type of topology is that the hierarchy can potentially create single points of failure, and links at the top of the topology, in the core, can become oversubscribed. Modern data center network operators have observed that as you move from the bottom of the hierarchy up towards the core, that the links at the top can carry as much as 200 times as much traffic as the links at the bottom of the hierarchy. So there's a serious capacity mismatch in that the top part of the topology has to carry a whole lot more traffic than the bottom. We'll explore how modern data center network architectures address these various challenges, but let's first take a quick look at one way of solving the scale problem. Recall that the scale problem arises because we have tens of thousands of servers on a flat Layer 2 topology, where all of the servers have a topology-independent MAC or hardware address, and thus, in the default case, every switch in the topology has to store a forwarding table entry for every single MAC address. One solution is to introduce what are called pods, and assign pseudo MAC addresses to each server corresponding to the pod in which they're located in the topology. So in addition to having a real MAC address, each server has what's known as a pseudo MAC address, as shown in pink. Thus, switches in the data center topology no longer need to maintain forwarding table entries for every host. They only need to maintain entries for reaching other pods in the topology. Once a frame enters a pod, the switch then, of course, has entries for all of the servers inside that pod, but they don't need to maintain entries for the MAC addresses for servers outside of each pod. For example, the switch in pod 1 only needs to maintain entries for these two servers with MAC addresses A and B, but it doesn't need to maintain independent entries for the servers with MAC addresses C and D. It only needs to maintain an entry for how to reach pod 2. Likewise for pods 2 and pods 3. Now, in such a data center topology, of course, these hosts are unmodified, so they're still going to respond to things like ARP queries with their real MAC addresses. So we need a way of dealing with that, as well as a way of mapping pseudo MAC addresses to real MAC addresses. The solution is as follows. When a host, such as server A, issues an ARP query, that query is intercepted by the switch. But instead of flooding that query, the switch intercepts the query and forwards it to an entity called the Fabric Manager. The Fabric Manager then responds with the pseudo MAC corresponding to that IP address. Host A then sends the frame with the destination pseudo MAC address, and switches in the topology can forward that frame to the appropriate pod corresponding to the pseudo MAC address of the destination server. Once the frame reaches the destination pod, let's say in this case pod 3, the switch at the top of that pod can then map the pseudo MAC address back to the real MAC address, and the server that receives the frame receives an Ethernet frame with its real destination MAC address, so it knows that the Ethernet frame was intended for it. By intercepting ARP queries in this way, and providing a mapping between topological pseudo MAC addresses and real physical MAC addresses, we can achieve hierarchical forwarding in a large Layer 2 topology without having to modify any host software. In this lesson, we will look at how data center traffic engineering, through customized topologies and special mechanisms for load balance can help reduce link utilization, reduce the number of hops to reach the edge of the data center, and make the data center network easier to maintain. We saw in the last lesson how existing data center topologies provide extremely limited server-to-server capacity because of the oversubscription of the links at the top of the hierarchy. Additionally, as services continue to be migrated to different parts of the data center, resources can be fragmented, significantly lowering utilization. For example, if the service denoted by green is running mostly in one part of the data center, but there's a little bit of it running on a virtual machine in another part of the data center, this might require traffic to traverse links of the data center topology hierarchy, thus significantly lowering utilization and cost efficiency. Reducing this type of fragmentation can result in complicated Layer 2 or Layer 3 routing reconfiguration. What we'd like to have is just the abstraction of one large Layer 2 switch. This is the abstraction that VL2 provides. So VL2 has two main objectives. One is to achieve Layer 2 semantics across the entire data center topology. This is done with a name location separation and a resolution service that resembles the Fabric Manager, which we talked about in the last lesson, and which is described in more detail in the paper. To achieve uniform high capacity between the servers and balance load across links in the topology, VL2 relies on flow-based random traffic indirection using Valiant load balancing. Let's take a closer look at how that load balancing works. The goals of Valiant load balancing in the VL2 network are to spread traffic evenly across the servers and to ensure that traffic load is balanced independently of the destinations of the traffic flows. VL2 achieves this by inserting an indirection level into the switching hierarchy. When a switch at the access layer wants to send traffic to a destination, it first selects a switch at the indirection level to send the traffic at random. This intermediate switch then forwards the traffic to the ultimate destination depending on the destination MAC address of the traffic. Subsequent flows might pick different indirection points for the traffic at random. This notion of picking a random indirection point to balance traffic more evenly across a topology actually comes from multiprocessor architectures and has been rediscovered in the context of data centers. So in this lesson, we have explored how Valiant load balance can be used on a slightly modified topology to achieve better load balance than in traditional fat tree networks without an indirection layer and Valiant load balancing. In the next lesson, we'll look at how a custom random topology can make some of these traffic engineering problems even easier. In this lesson, we'll look at Jellyfish, a technique to network data centers randomly. The goals of Jellyfish are to achieve high throughput to support, for example, big data analytics or agile placement of virtual machines, and incremental expandability so that network operators can easily add or replace servers and switches. For example, large companies like Facebook are adding capacity on a daily basis. Commercial products make it easy to expand or provision servers in response to changing traffic load, but not the network. Unfortunately, the structure of the data center networks constrains expansion. Structures such as a hypercube require 2 to the k switches, where k is the number of servers. Even more efficient topologies, like a fat tree, are still quadratic in the number of servers. By looking at this figure showing a data center topology where the servers are at the edge of the graph, can you try to figure out where data center topology primarily constrains expansion? Is it at individual servers, aggregation switches, or top-level switches? As we can see from the figure, most of the congestion occurs at the top level. Jellyfish's answer to how data structure constrains expansion is to simply have no structure at all. Jellyfish's topology is what is called a random regular graph. It's random because each graph is uniformly selected at random from the set of all regular graphs. A regular graph is simply one where each node has the same degree. And a graph in Jellyfish is one where the switches in the topology are the nodes. In contrast to the earlier data center topology diagram we saw, here is a picture of a Jellyfish random graph with 432 servers and 180 switches. Every node in this graph has a fixed degree of 12. Jellyfish's approach is to construct a random graph at the top-of-rack switch layer. Every top-of-rack switch I has some total number of Ki ports, of which it uses Ri to connect to other top-of-rack switches. The remaining Ki minus Ri ports are used to connect servers. With n racks, the network then supports n times Ki minus Ri servers. And the network is a random regular graph denoted as follows. Formally, random regular graphs are sampled uniformly from the space of all R regular graphs. Achieving such a property is a complex graph theory problem, but there's a simple procedure that produces a sufficiently uniform random graph that empirically have the desired properties. To construct a Jellyfish topology, one can simply take the following steps. First, pick a random switch pair with free ports for which the switch pair are not already neighbors. Next, join them with a link and repeat this process until no further links can be added. If a switch remains with greater than or equal to 2 free ports, which might happen during the incremental expansion by adding a new switch, these switches can be incorporated into the topology by removing a uniform random existing link and adding links to that switch. For a particular equipment cost, using identical equipment, the Jellyfish topology can achieve increased capacity by supporting 25% more servers. This higher capacity is achieved because the paths through the topology are shorter than they would be in a fat tree topology. Consider a topology with 16 servers, 20 switches, and a fixed degree of 4 for both the fat tree topology and the Jellyfish random graph. In the fat tree topology, only 4 of 16 servers are reachable in less than 5 hops. In contrast, in the Jellyfish random graph, there are 12 servers reachable. By making more servers reachable along shorter paths, Jellyfish can increase capacity over a conventional fat tree topology. So while Jellyfish shows some promise, there are certainly some open questions. First, how close are these random graphs to optimal in terms of the optimal throughput that could be achieved for a particular set of equipment? Second, what about topologies where switches are heterogeneous with different numbers of ports or link speeds? From a system design perspective, the random topology model could create problems with physically cabling the data center network, and there are also questions about how to perform routing or congestion control without the structure of a conventional data center network like a fat tree.